Okay, so today what we're going to be going over is chapter 22, which is our non-metallic elements and their compounds. Now, to be honest, this chapter is a little bit straightforward. We're not going to do too much about it. It's more like a recap of, in the same way that the atmospheric chemistry chapter, chapter 20 was kind of a recap of different things and their applied chemistries. Chapter 22 is a little bit like that. So what we're going to be looking at this time is we're going to be looking at our metalloids and our non-metallic compounds. And specifically, we're going to focus on hydrogen, carbon, and nitrogen as our big ones. So this is really just a final add-on so that way you can see some of these chemistries in motion. I think a big part of this class is to kind of expose you guys to how you see some real-life chemistry going on. I've also included some videos in our course webpage so that way you can follow up on some of these topics if they're interesting to you, right? Like synthetic diamonds, how are they made? The hydrogen economy, and things about the Barn-Haber process, right? So let's look at this first part. This is a little bit of a review from Chem 120. And so we want to think about which of these following exists as diatomic molecules in their most common elemental form. So when we look at these, we want to think about which one are diatomics. That means that there are two atoms making one molecule, and that should be our chlorine, hydrogen, and nitrogen. So all of those exist as diatomics. So the first chemistry we're going to talk about is our hydrogen. Now, hydrogen forms compounds with our metals and our nonmetals. When it forms them with our metals, we call them hydrides, and that could be things like our lithium, sodium, potassium. And they get that name because in those compounds, our hydrogen, instead of being a positive like it is with our nonmetals, is really taking on a negative role. With our molecule side, so when it partners with our nonmetals, then hydrogen normally takes on that positive one. And so the hydrides can take on some unique type of chemistry because we have a negative H, which is a little bit unique for that situation. And a lot of the ones that we look at are things like beryllium and aluminum hydride, and they have some interesting chemistries that happen with that. So when we look at things like sodium borohydride, we want to think about what the oxidation state of that boron is going to be. So sodium boron hydride should be Na, V, or an H2 there. So let's look at that and let's think about what our oxidation state should be for sodium borohydride. And I realize I made a mistake there. It's not H2, it's H4. And now we should be able to figure out which one it should be. Right? So it should be, sorry, H4 there. And so when we're looking at that, our sodium is going to be a +1. Our hydrogens are going to be -1, and there's 4 of them. So we should have +1 plus our boron -4 is equal to 0. And so our boron must be a +3 in order to make that work. Now, hydrogen comes in several different isotopes. We can have our normal hydrogen with the mass number of 1. We can have deuterium with a mass number of 2. That means it's got an extra proton there, or not proton, an extra neutron. Or we can even have tritinium, which has a mass number of 3. Now, our isotopes of hydrogen can have a big impact in different things because they can make things like D2O, which is what we label as heavy water. And while it can be incorporated in a lot of the same chemistries as our H2O, it does play a different role in its bonding because its mass is so much larger compared to that of that hydrogen. Now, it can form actually stronger bonds with our hydrogen, and so it can lead to slightly different chemistries. You can even see it down here in terms of its rate impact. It adjusts the rate of a reaction just a little bit, so it's a little bit slower to deprotonate compared with our other ones. Now, the interesting part about it is that while it's similar enough that it can be incorporated in a lot of chemistries, it's different enough that it gets incorporated in slightly different ratios. And so we use deuterium to do a lot of tracing with MRI. So that's like a magnetic resonance imaging. And so we can ingest this and we can follow how it responds inside of your body, and we can track those different biological processes. Now, D2O can be hazardous to your health. There hasn't been a study about exactly how much you need to ingest in order for it to be hazardous. There's some that claim that it has to be as high as 50%, others that claim it can be as low as several cups. And it really just depends. No one really quite knows. And part of that problem is because deuterium is actually very expensive to produce. It does happen naturally or as a result of nuclear reactions. But most commonly what we see is you can concentrate it by doing some electrolysis, where you will consume all of the H2O as you split it. And so the natural occurrence of D2O will slowly build up over time, as the D2O doesn't electrolyze as quickly as the H2O. So when we think about it, the most prevalent isotope of hydrogen, is it going to be protonium with just one proton, deuterium with a neutron, tritinium with 2 neutrons, or quaternium with 4? We should all know that it should be our 1H is our most prevalent isotope. Now, we talked about hydrogenation inside of chapter 24, and it is an important part, and so we do want to remember that. And hydrogenation is the addition of hydrogen to a compound containing multiple bonds. So this is how we can take an unsaturated compound and we can saturate it. Now, this is a really useful part as we want to turn on and turn off different reaction sites. A double bond is a good reaction site, but if we want to take that away, then we might want to use that hydrogen in order to hydrogenate that compound and saturate it and make it more stable. Now, we do use a platinum catalyst for this to help facilitate that process. And so this is an example of those platinum catalysts. So let's think about what the oxidation states are for these hydrogens as we look at this series of reactions. So in this one, we definitely have a +1 here. And this one is going to be a 0 for that molecule. We have a +1, a 0. We have a +1, we have a 0. We have a +1 again, we have a 0, and we have a +1, we have a 0. This one is also a +1. And so it looks like the only options we have is both +1 and 0. So we're looking at D. And so you can see here that we don't have any of those hydrides. Right? We don't have any where we're partnering that hydrogen with our metal in order to make it a -1. And that's more chemistry that we're more familiar with. Now, hydrogen production can be produced in a couple of different ways, right? The most common one right now is actually through water splitting, where we take H2O and we do an electrolysis reaction, similar to this one down here. Or sorry, that is like our cleanest way and a growing way to make hydrogen right now. But in reality, one of the other more common ways that we make hydrogen right now is through the use of fossil fuels. And we can combust it down in order to make carbon monoxide or reduce it down and a hydrogen gas. We can do that with coal. We can do that with methane. We can do that with longer chain hydrocarbons. Another common one that you've probably done before is when we add in zinc to an acid, and that can produce hydrogen. And so it depends on kind of what scale you're doing these. These top two are more in our industrial scale. And the reason why they're done so easily right now is because carbon monoxide can be a very useful material. There's a need for carbon monoxide as it's a good reducing agent. Also, we have a prevalence of coal and hydrocarbons in our industry settings, and so they're very familiar and they can be worked with quite well, so it's an easy process for them to coordinate that and to build that. On the benchtop scale, we might have these zinc processes where we might be trying to make pure hydrogen, It's easy reaction to do, it's easy to control, it happens quite quickly. But on an industrial scale, you don't see it as often because it's cheaper to get coal and water than it is to get zinc metal and hydrochloric acid. Now, there is this thought about moving towards a hydrogen economy, and it's because hydrogen can be fairly easy to make and it has a really high fuel value. That means that per gram, we can get a lot of hydrogen out. Now, with electrolysis and the ability to split water into hydrogen and oxygen, the fuel economy, the hydrogen economy was gaining steam about 10 years ago. The challenge with it is not only is it making that hydrogen in a very green way, right, or with minimal impacts, it's also about trying to make it cost effectively. And then the other part with hydrogen that becomes a challenge is the storage and transportation of it. So it still is used in some cases. You can get a hydrogen fuel cell car, right, where you use hydrogen as your energy source instead of things like gasoline. There are also power plants where they are looking at using hydrogen as a storage. So instead of storing it as a battery, you might store it as hydrogen and then burn it in order to get your electricity at a later time. And so there's a lot of different thoughts about the hydrogen economy. It just never quite took off in the way that people expected it to because of these challenges with storages and transportation. It also didn't help that natural gas and gasoline plummeted in the price during that time as well. So then hydrogen production was hard to compete. It's hard to make it at the same price point. Plus, there's a lot of infrastructure that would have to get transitioned over into hydrogen for a hydrogen economy to work. Now, hydrogen is also very commonly found throughout our solar system, and it has some big impacts on that. If we look at Jupiter, Jupiter is almost entirely made up of hydrogen. Now, it's interesting because in its core, it's such a large planet with such high pressures that it actually has a metallic core of hydrogen. Then we also have a metallic molecular hydrogen, and then we have the molecular hydrogen on the outside, so the gases that we're more used to seeing. And so the planet's magnetic field is produced by this movement of the electrically conductive fluid on the interior. Now on Earth, we're a rocky planet, and so we have iron on our interior, but hydrogen makes up a large part of our gas giants. So those are those planets that are farther out past Mars, where they are primarily made of gases, and primarily it's going to be hydrogen on that level. So if H2 is activated to produce H+, what has to be the other product? So if we're taking H2 and we're making that into H+, what would that missing one be? And so when we activate it, if we're using H2, then our missing one is going to be our H-. So we're going to make a hydride. And so this is one way for us to make hydrides, which we can then react with our metals to form those binary hydrides that we looked at in the beginning. Now, the second material that we're going to look at is carbon. Carbon is a very common element for, sorry about that. Carbon is a very common element for chemistry. We use it a lot in our organic materials. It's actually so commonly used by living species that organic chemistry is all about compounds containing chemistry. Now, carbon shows up in a lot of different forms. You can have it as a vapor. You can also have it as coal. And primarily, its most stable state is actually as this form graphite. Now, graphite is a slightly more ordered structure than coal. And so it requires slightly different conditions when we make it. And the most stable, or not the most stable, but another additional form is the diamond. So carbon can also be used in a diamond form. The difference is that diamond requires really high temperatures and really high pressures in order for it to achieve. Now, once it's made, diamond ends up being quite stable, even when we move it down into the range where it would normally be graphite. And so you can think about why that might be. even if it's in the higher energy form, right, where it should be graphite at that state. If we were to make carbon solids at that state, we will form graphite. Instead, that diamond can sit there and exist for a long period of time. I also find it interesting that now there is this growing movement towards make synthetic diamonds. Now, when your book was written and they were discussing this, a lot of our diamonds were, the synthetic diamonds were made in a poor quality, and so they were yellow, and so they didn't really look desirable in the same level that natural diamonds were for jewelry conditions. But that in technology has kind of improved, and you can get a much clearer and higher quality synthetic diamond now than you used to be able to do. And so that would be something that if you're interested in, I've linked a video where they kind of discuss how you might go about making a synthetic diamond in the laboratory. So if we think about why this might be, graphite is the most stable form of carbon under normal conditions. Are we worried about diamonds disappearing? And so if you've had a diamond, you can tell that it hasn't really degraded over time with light, so you don't really have to store your diamonds in refrigerators. And so when we're looking between these two processes, what's going on is that graphite, or that conversion into graphite, is a really slow process. If we were to think about why that is, if we are starting out as a diamond, that means we're covalently bonded to all of these other three-dimensional sheets around us for our carbons. In order for us to transition from that into graphite, where we're just single layered sheets, we would have to break apart these strong covalent bonds. And so we have a high activation energy. That doesn't mean that it can't happen. It just means that our rate is going to be quite slow as we wait for that to happen. So it's not that the diamonds need a protective coating. It doesn't need to form an oxide layer. They themselves have such a high initial energy, activation energy, because of those strong intermolecular forces between them. Now, carbon can be used for a lot of different things. We have our diamonds, we have our hydrocarbons that we use for coal and gas. But there's another one that I kind of want to bring to your attention. It's called the Fischer-Tropsch process. And what this is this is how you can use coal to make synthetic hydrocarbons or longer change carbons. So you can take coal and you combine it with water to make it into carbon monoxide and hydrogen. So that's very similar to the reaction that we saw at the hydrogen production. But then what you can do is you can take that and you can combine it with more coal for that hydrogen to turn it into methane. You can take that carbon monoxide and you can combine it to form methanol. And so over time, you can build longer and longer chains of that carbon by adding in more and more of that carbon monoxide. So this was something that arose from research in Germany when they were looking for an oil alternative. And this, I believe, was back during World War II, when they were looking, it was either World War I or World War II, when they were looking at options so that way they wouldn't become gasoline, like run out of gasoline if they couldn't import any more oil. Sorry. And so today we can, like the majority of South Africa's diesel is made using coal because when the oil costs go over $43 per barrel, synthetic diesel becomes less expensive than conventional diesel if we were to make it using this Fischer-Tropsch process. But we can use this to make any type of straight chain carbons, going from carbon 10 all the way up to carbon 15s from coal. So this is an alternative there instead of using oil. It's not a very clean alternative. It does produce carbon dioxide still in that process. We're still burning coal, but it is an alternative there as we look to transition towards making different types of options. The last compound that we're going to discuss is our nitrogens. Now, our nitrogen compounds, they exist in a whole variety. We have ammonia, which is probably the most common compound, or nitrogen-containing one. But we can also have things like hydrazine, which has two of these hydrogens right next to, or not hydrogens, two of these nitrogens right next to each other. We can also have it with our nitrogen oxide. We also have things like nitric acid. Now, our nitrides are really strong compounds because they form these really strong bonds with this high charged nitrogen. So ionically, nitrogen can make very strong bonds because it can support a very large charge for its size. Ammonia is a very important compound. It's probably one of the most important compounds because it's used in fertilizer. We need to use ammonia in order to help plants grow because the plants need the nitrogen fixing. So they need nitrogen from their soil in order to be incorporated into their processes. And so ammonia is going to be a big production process. And so we go through and we make a lot of synthetic ammonia. About 70% of the world's ammonia, or sorry, of your nitrogen in your body comes from this production of ammonia. Hydrazine is another common compound. Hydrazine is a strong reducing agent because it really wants to go down to nitrogen gas as its more stable state. And so it can do some interesting chemistries. So about 3/4 of the ammonia produced in the United States is used in our fertilizer because we use it for food production. So in your in the Canvas, I have a video that discusses the production of ammonia using the Haber-Bosch process and why that's such an interesting process. It was actually thought to be the most influential chemistry process developed in some ways because it's been able to account for a huge boom in food production, which has also accounted for the huge boom in population. Right? Before that, if we're not able to produce food to feed everyone, then our population size is limited. The oxides are used for quite a bit of different processes. They naturally occur through our nitrogen fixation process, and so we use that when we're trying to take nitrogen gas, and we can react it with oxygen to form a compound that can then be used. But you can also use it for things like laughing gas. So if you've ever gone to a dentist and they've put you under, right, they can use nitrous oxide for that. And so nitrogen has a lot of different types of uses for it as well. This is going to be, if you did Chem 120 and you did a cycle of of copper reactions, one of the things that you did was you made nitrogen dioxide by taking that copper solid and mixing it with nitric acid to dissolve it. And so nitric acid is actually a very strong acid in that it can oxidize a lot of different metals in order to dissolve them. You can actually use nitric acid with a couple of different other acids to dissolve things like gold and even silver. And that's because it's that extra strong oxidizing agent. It can be used for our zinc, for our silver or gold, because it can make these compounds that are soluble, and it can help continue to oxidize them, not just because of the NO3, but even, or not because it's just an acid, but also because of the nitrate that is produced with it. And so let's look at the oxidation numbers for our different nitrogen atoms. We have nitric acid and we have nitrous acid. And so we want to write out those compound formulas first. So nitric acid is HNO3, and nitrous acid is going to be HNO2. Sorry. So if we want to look at our oxidation numbers, our hydrogen is a +1, our oxygen, there's 3 of them, and they're both -2. And then we have our nitrogen, and all that's got to be equal to 0, so +1. And then this time we only have -2 oxygens. So this becomes 1 minus 6 plus nitrogen equals 0. So our nitrogen must be a +5. And then we have 1 minus 4 plus nitrogen equals 0. So our nitrogen must be a +3. So in nitric acid, we should be +5. In nitrous acid, we should be +3. And so that's basically all we need to know about our carbon, nitrogen, and hydrogen atoms. So I would encourage you to watch the videos just so that we can see a little bit more of how this is in work, or done in work. For the quiz and your exam questions from this chapter, what I would refer to is your homework problem, so you can see kind of what that looks like. It's less about trying to memorize these reactions and more just about trying to get you guys exposure of these reactions applied to real life settings. So I would be providing you with information, like I would tell you the reaction process, but it's about trying to help you utilize that information to apply it into an industrial setting. So this is more about exposure and less about memorizing all these things. I'm just hoping that you can see some of this chemistry in action and help you connect with it.